Here is an abstract state feedback tracking controller. Let's suppose the process is subject to noise in the state equations and the measured output. Then, for a hypothetical two-state system, the output will be noisy. Apart from dealing with the noise, what if additionally we only had partial state feedback, but our controller relied on full state feedback, ideally clean signals? How could we estimate the full state from partial information and filter the noise? We could use the well-known Kalman-Bucy filter, also just referred to as the Kalman filter. In this lesson, our goal is to learn basic probability ideas as applied to noisy, time-varying signals for future development of Kalman filter state estimators. We'll work with noisy signals drawn from stochastic processes, or a statistical process that evolves with probabilistic laws. So, let's consider this noisy signal. The noise is characterized by random fluctuations that have probability of occurring over a sample space. The sample space is just the space of all possible outcomes for each random draw. Specifically here, it's -1 to 1. Now, how could we estimate the probability of the signal having a value between 0.2 and 0.4? We could see how many times this signal lied within the interval 0.2 to 0.4. To view this, we divide up our sample space into bins. Then we put each sample into the corresponding bin. This is fun to watch. It's like a race. Which bin will win? We see between 0.2 and 0.4, there are over 50 samples out of a total of 500 samples drawn. So we would speculate the probability is just over 1 in 10. This diagram is called a histogram. It's comprised of a bunch of little rectangles. The height of each one is a single sample, and the width represents the size of the bin. So again, we ask, how can we estimate the probability of a sample falling into the bin between 0.2 and 0.4? Well, it's again how many times the event occurred divided by the total number of samples. As an estimate, we'll call this probability P7, corresponding to the bin number. Now, mathematically and more specifically, how can we write this probability? First, let's introduce a function denoted 1 defined over minus infinity to a value a. This function has a value of 1 if the sample xi is less than a, otherwise it's 0. So the total number of samples up to a is simply the sum of the function 1 evaluated for each xi. We simply divide by the total number of samples to get then the fraction of samples up to a. This formula is called the empirical cumulative distribution function. It's assigned the variable f. The tilde indicates the result is empirical based on data, and the subscript n indicates it depends on how many samples are taken. Now we can use the empirical CDF to determine the probability of a sample landing in B7. It's simply the difference between the CDF at x6 plus h and the CDF at x6. The result is the total number of samples in B7 divided by the total number of samples drawn. Then we can do this for each bin and come up with each bin's probability. And if we divide each bin's probability by the bin width, we get a uniform approximation of probability per unit x across each bin, so that overall bins, we have a piecewise constant approximation of the probability density function from data. And this approximation gets better as the number of samples increases. 500 samples, 1,000, 10,000, 100,000, 1,000,000, 10 million, until ultimately we observe this PDF approaching a uniform, constant probability density of 0.5 over the sample space -1 to 1. We call this a uniform distribution, and it governs some natural processes like rolling dice or mixed balls being pulled for lottery drawing. We can integrate this PDF over an interval then to find the probability of a sample landing there. For example, between 0 and 1, there's a 50% probability that the sample will fall on the right-hand side. And if we integrate over -1 to 1, we get 1, because that's just the sample space, and by definition, the sample lies within it. So far we've looked at the probability of a sample falling into an interval. Now consider our previous noisy signal. If we take an additional sample in the series, what value should we expect to get? If we assume the statistics of the process that generated this signal do not change with time, then we can estimate the expected value of the next sample from the mean value of the given data set. Consider another perspective. Instead of evaluating statistics across time, we could look at statistics of a data point at a specific fixed time. We'll assume that the statistical properties of the data do not change. That is, the stochastic process that generates this data is stationary. So we pick out a point in time, say ti, and observe the variable x of ti. Then, if we generate multiple sample series from the same stochastic process, each time picking out x of ti, we will find the same mean of x of ti as we would evaluating the mean across the entire time series. And we can link this mean to the probability density function. Consider for the moment that our previous PDF corresponded actually to 10 discrete outcomes, x1 through x10. If we multiply the PDF of achieving one outcome, f of xi, by that outcome, xi, we get the probability of xi occurring. That probability contributes to the expected value, or the mean, of x. By weighting each outcome, xi, by their estimated probabilities, we get the mean, or equivalently, the expected value of the random sample. This summation is essentially a discrete integration of the product of x and the PDF over the sample space. In the continuum, this is the integral of x times the probability density function over the real line. For our uniform distribution, we find our mean or expected value is 0. In addition to the expected value, we would like to quantify how much a signal should be expected to vary from its mean. Mathematically, we can quantify the variation of each sample as the difference between the sample and the mean of the dataset. For a useful measure of variation, we square the difference. Otherwise, the signal could vary greatly in both positive and negative directions, canceling each other out, indicating no variation. Now, if we take the expected value of this measure, we get the definition of variance, denoted here as sigma squared. Variance depends on a single variable, and it captures the mean variation from the sample mean. The square root of the variance is the familiar standard deviation. Let's explore variance a little further. Expand the product, distribute the expected value, factor out constants, substitute the mean, simplify, and we have that variance is actually the expected value of x squared minus the mean of x squared. For our random signal with a uniform distribution, its evaluation is 1/3. And on the PDF, there's 3 variances to the width of the sample space. So far, variance was introduced for a single signal. How can we expand the notion of variance to multiple signals? Let x be a vector of m separate, time-varying random signals. These will have their own means, their own variances. If each signal in x is a stationary process, then each signal evaluated at any point in time will have the same statistics as the overall time-varying data set. And we can compute the PDF from the data set for each signal. That is, the blue time signal corresponds to the blue PDF, the magenta, the green, and so on. Here, I've used the same process to generate each noisy signal, so that the empirical PDFs indicate the same continuous PDF of 0.5 over -1 to 1. Of course, each PDF is not necessarily the same. These signals can vary greatly and are assumed to be independent of one another. Variance of each signal involves the product of each signal with itself to give an indication of how much that signal varies. Since these noisy signals are zero mean, the variance simplifies to expected value of the signal squared, giving again 1/3 for a uniform distribution of 0.5 over -1 to 1. But what about how much one signal in x varies with respect to another signal? Since we're talking about the variance of 2 separate signals, this is termed the covariance, as in the joint variance. For these specific signals, again, the means are 0, so their covariance is simply the expected value of their product. In this example, both signals are generated from the same stationary process, so that while their statistics are the same, they vary randomly with respect to each other. Hence, they don't move together more often than they move in opposite directions. So there's no correlation between how they move together jointly. Thus, their covariance is 0, and the signals are said to be uncorrelated. We may also want to look at the covariance between 2 signals, say at different times, t1 and t2. Again, in this case, both signals are generated with the same stationary process, a uniform distribution. So if we were to repeat the signal draws multiple times to collect multiple x1 at t1s and x2 at t2s, we would find they would have the same statistics as the signal x1 and x2 respectively. As before, the signals are generated from a random uniform draw between -1 and 1, so this example has a covariance of 0, and the signals are also uncorrelated. Now consider we are dealing with the vector x and its corresponding vector of means. To construct all possible product combinations, we take the outer product of the 2 vectors, producing an m by m matrix. And then, taking the expected value of the matrix, it distributes to each element, creating a matrix of variances on the diagonal and covariances elsewhere. These elements capture whether the variations in the signals tend to move with respect to one another or not for every possible combination of signals in the vector x. This is known as the covariance matrix. It contains multiple variables, capturing how much the fluctuations in one variable are correlated with another. With the signals x1 and x2 given, the covariance matrix ultimately depends on just the difference between the two times t1 and t2. We can investigate the covariance matrix similar to how we expanded the scalar variance. First, expand the product, then distribute the expected value to each term, factor out the constants, replace expected values with means, and finally simplifying. We get the covariance is the expected value of the outer product of x1 and x2 minus the outer product of their means. The first term on the right-hand side is called the joint moment matrix. It's like a covariance matrix, but the means are not subtracted from x. This also captures how much one variable moves with respect to another. And if x contains zero mean signals, then the covariance matrix is the same as the joint moment matrix. We've seen how to construct a covariance matrix for multiple variable inputs in x. What if we were to use this same approach, but to correlate x with itself at multiple different points in time? Let x be a scalar evaluated at n points in time, where each x of ti has its own statistics. How does the variable x of t1 correlate with x of t2? We can follow the same process as before, taking the expected value of the outer product of the vector x to produce another matrix, this one R denoted with two x subscripts. It's called the autocorrelation matrix, and it represents the correlation of a variable to itself at different points in time. Uncorrelated elements will have zero autocorrelation. If x has no mean, this has been called the autocovariance. So far, we've discussed the covariance matrix, the joint moment matrix, the autocorrelation matrix, and some other statistical definitions. I've found that some textbooks use different names for the same matrix, such as the correlation matrix instead of the covariance matrix. Luckily, in such textbooks, you'll get a definition of what's intended mathematically. This lesson is not meant to be the authoritative source of definitions. Instead, it's intended to allow you to understand how to interpret the definitions of others, whether it be the same as what's presented here or different. Regardless of what things are called, each matrix here is bound by a common theme: how to quantify signals variation with respect to each other. Up to this point, we've examined these matrices with signals having a uniform distribution. I would be remiss if we neglected the important and well-known normal distribution or Gaussian distribution. Here, 500 random samples are drawn from a normal Gaussian process. What do we observe? Their values tend to be centrally located. Fewer values occur away from the central tendency. Increasing the number of samples, we see a beautiful bell-shaped curve. Then, calculating the empirical probability density function, we find that it matches the analytical form of the Gaussian distribution very well. Note the distribution can have many bell curve shapes depending on the mean and standard deviation. The Gaussian distribution is important because it appears in many natural phenomena, like the height of people, measurement errors, Brownian motion. Suppose, for example, we're measuring the height of a group of people. Each measurement has its own uncertainty. These uncertainties could come from the posture of the person, the resolution of the measurement tool, possibly even the technique of the person doing the measuring. But ultimately, we come up with a set of height measurements for a group of people. This signal, the heights of the individuals, will have their own statistics. And let's presume here that they're not necessarily a Gaussian or a normal distribution. For the present n set of people, though, we take that set of data and we determine the mean or the expected value. Now we'll call this sampled mean x bar, and we'll use it as a single data point for the variable height of people. Now suppose we go outside, we get another group of people together, and we measure their height. This would be a second data point for height of people. And we keep doing this. If the number of observed averages is large enough, the resulting distribution becomes normal or Gaussian. This example shows how a Gaussian distribution emerges from mean data, even if the underlying samples used to create each mean is not Gaussian. As a side note, this is an illustration of the central limit theorem. Gaussian distributions are important because aerospace systems rely on sensor measurements with uncertainty. So the assumption of Gaussian noise is common. With the basic concepts in probability theory in this lesson, we can now take a step toward analysis and simulation of noisy signals and feedback control systems. In future lessons in this series, we will learn how to determine the response of linear systems subject to noise. We will also learn how to construct the Kalman filter. This will require application of statistical ideas in this lesson. Finally, we will discretize the Kalman filter and controller to simulate the discrete compensator with the continuous process dynamics. In the guidance homing loop, the Kalman filter is important because it can filter noisy measurement data and can estimate full state data from partial information that is not otherwise available. Access this lesson and more at learngnc.com. And I'd like to thank each one of my Patreon subscribers who gain access to the codes in this analysis, lesson previews, video discussion, and code tutorials. You make this content possible. Thank you very much.